Hi there, I'm Dr. Nathaniel Davis from Victoria University of Wellington and the MacDiarmid Insitute, and I've been asked to do a follow-up video to my previous video that I did for the New Zealand Institute of Physics, where I talked a bit about my research and how it fits in the field of physics. This follow-up video is just going to look at some of the advanced concepts that we briefly touched on in the last lecture, and also I'll briefly talk about what it takes to be a research scientist. So what I mentioned before was that how all the science fields overlap, but it's also bigger than that. One of the main things that underpins all science research is scientific method, and that's sort of the analytical skills that you need and require to do any of this research. Maths is also very important. It links into everything. Even biologists use maths for the statistics. Basically use math to prove that your result is real, because you need to show that it's statistically relevant. And one of the big things that I forgot to mention was also English. So if you look at a scientific paper, these are the papers I published last year. I think there's, say, 7 or so, but these are all 7 pieces of written work. So though I'm a scientist, I still do write every day, and I write the equivalent of essays is how I get out my science to the public. So they're usually between 5 to 15 pages. You can see they contain quite a lot of text, some equations, and also some data. They're structured similar to how you'll be learning in class. There's introductions, there's methods, there's results and discussions and conclusions, and so it follows a sort of standard scientific paper methodology that you would learn for any science class. They also contain detailed graphics. We start using graphics software here. This one was made in Blender to make 3D shapes and molecules. So you don't just have to know maths and English, you also have to know a little bit of graphic design if you want your papers to look really nice. So in summary for this, science is a combination of everything, but you also don't have to know it straight away. You don't have to be good at it straight away. In high school I was terrible at English. I didn't find it interesting. I wasn't very good at analyzing written text because I found it boring, and I was interested in science. I wish I paid more attention back then, because I'm actually using a lot of the skills I would know in English now to write my papers. But with a good understanding of English and maths, and also this scientific method, you can explore any combination of these research fields. So now moving on to covering some of the sort of advanced concepts that I briefly discussed before. The first is how solar panels work. So you should all know about electrons. So electrons are the little subatomic particle that orbits around your atom, and they're what conduct electricity. And so the way a solar panel works is a thing to do with electrons and holes. So you have an electron, which is promoted by a photon from your valence band to your conduction band, and that can move around, that conduct electricity, right? Because there's no more electrons around here, it conducts electricity, but down here there's too many electrons in the way, so the valence band is non-conductive. What a hole is just the absence of an electron. So if you imagine this electron here moves across, now you have a hole here, and then this electron moves across, now you have a hole there. So holes work pretty much exactly like electrons, except that it's the absence of electron. And if you treat them as their own particle, all the maths and physics work out. But so what a solar panel does is a photon creates this electron-hole pair. The way you get this current, because of course you can't just have this recombining, that could just go back down and emit a photon, it can luminesce. To get this current, you need an internal bias. So what happens here is we have our doped semiconductors. So what you do is you make one slightly more positive and one slightly more negative. So you add some holes in, or you add some electrons in, using a different material. Then what happens when your electron is promoted to conduction band? It will be dragged down because electrons want to relax, and holes will be dragged up. And that's going to make this internal bias. And that's how solar panels actually work. The photon promotes the electron, and the electron undergoes this internal bias built in within the actual material. That's why there's normally drawn electrons going up, holes going one way, and that makes your electric current. I didn't really cover relaxation properly, so this is actually called thermalization. And so what thermalization is when you have a high energy electron or photon promotes your electron high into the conduction band. The way it relaxes down is through thermalization, and what that is tiny minuscule vibrations, and these release phonons. So a phonon's similar to a photon, but it's a vibrational state, so it's a quantized unit of vibration. And so as it goes down, it releases phonons, and that's how it loses its energy. But it those phonons, which are vibrations, then correspond to heat. So you can say that the energy is lost as heat, that it relaxes, or it thermalizes down to the band gap is sort of the more correct way to say it. What we then also discussed was this trade-off between having enough energy to promote our photon from our electron from our valence or conduction band, and not having too much energy that will lose that energy through thermalization losses. And what this is here is a graph of band gap versus the fraction of incident solar radiation and where it goes. So if we just look at the different types of losses here, we have these emission where the solar panel emits, these Carnot engines and angular dependence. I wouldn't really worry too much about them, they're a bit sort of more advanced topics. But you should be able to understand this cool and this sub-band gap. So this dark blue color is this case, where the photons don't have enough energy for the band gap, because that's what happens when we increase this band gap. We make this higher, and we get more sub-band gap losses. And this light green is this cooling, this thermalization. And so what we can do is we can shrink our band gap and make it really small, which means we absorb all the photons, but then this loss here, this excess energy, becomes more. So there's a trade-off between making your band gap small to get all the photons, but getting too much cooling losses, or increasing your band gap and getting rid of those cooling losses, but not absorbing enough photons. And that's what leads to the Shockley-Queisser limit, shown here in dark blue. So it's the one that gives us that 32% limit, because there's sort of like a Goldilocks region where you're absorbing enough photons and you're not losing too much energy. But that said, we are approaching the Shockley-Queisser limit. So this is a graph of all the different solar panels that have been produced sort of since 1975 to sort of 2020. I need to update this slightly. But ignoring these purple ones, the purple devices are multi-junction devices. So that means they're more than one solar panel glued together. And you have one solar panel absorb the low energy light and one solar panel absorb the high energy light. But this big red line here is the Shockley-Queisser limit, and you can see all of our different solar panels, if they're perovskites, if they're organics, if they're nanocrystals, if they're silicon, are all starting to approach this limit. So if we don't do anything soon, solar panels are never going to be able to get any better. And that's why we're looking at different ways to add or multiply photons. Just elaborating on the slide that had all these pictures, one of the ways we can do this is through multiple exciton generation. So an exciton is an electron-hole pair. So that's what we've seen. A photon promotes an electron into your conduction band. You have your hole. That's an exciton electron-hole pair. And multiple exciton generation, instead of you losing this energy as heat for thermalization, you actually use that excess energy to promote another electron across the band gap, which is from our valence to our conduction band. And the only real requirements for this is that this initial photon has twice the energy of our band gap. So you can go twice the energy, you can get another exciton generated. If you had 3 times the energy, ideally you can get 3 excitons generated. And then they just work like a normal solar panel, where your holes will go one way and your electrons will go the other way. Another way to do it is through an optical approach. This is called singlet fission. So singlet fission is a process and when you excite a molecule into its first singlet state. So it's a singlet compared to a triplet is just difference on their spin, if they're paired or unpaired electron spins. But the easiest way to know is that singlets can emit light, they're fluorescent, and triplets can't emit light because that's what you sort of have, a phosphorescence. So triplet states are what are in those little glowing stars that you put on your roof. They glow for a long time because it's a forbidden transfer. So you need to turn it back into a singlet if you want the light out. But in this process, you excite a singlet, you let that decay into 2 different triplets, and since there's 2 of them, they sort of add up to a singlet, so quantum mechanics is happy. And then you transfer that triplet into something that can emit a triplet, and then you get 2 photons out for 1 photon in. So instead of making a solar panel, which is what this case was, this is now sort of a film that would take blue light and produce twice as much red light. Up conversion uses singlets and triplets. This is via triplet-triplet annihilation. It's a very complex reaction scheme at the moment, but you excite a singlet, sensitize one molecule into its singlet state, and you do that twice. You then, through a couple of processes, convert that into a triplet, on another molecule, this emitter. And this emitter is special because its triplet state is half that of its singlet state. And then what you allow to happen is you allow these emitters to come together and they undergo triplet annihilation, where one triplet will drop down to its ground state, it's no longer excited, and the other triplet gets promoted up to its singlet state, which as we know now is emissive, and that will fluoresce the photon. So red light can come in, it can go into a triplet where it will stay there for a long time because it can't emit, just like those glowing lights on your roof, and then turn into a singlet, it'll quickly emit this bright yellow light. And so this would be another way to add photons together. We also looked at luminescent solar concentrators. So remember, these are bits of plastic or glass that absorb light and focus it to the edge. And I didn't really go into the details on how they focus it to the edge, which I'm going to do now. So it's all to do with waveguiding and total internal reflection. So you should all know about reflection because it's something we see every day. You can see reflection normally when you look at a material from a high angle. And that's because there's this angular dependence, where you have a surface which has a different refractive index. So that just means light interacts with it differently. So things like glass, plastic, water all have different refractive index compared to air, which doesn't really have this refractive index. So the light comes in and it can bounce off the surface. And that's what's happening in this picture. The light from the mountains is bouncing off the water and coming towards your eye. The way total internal reflection works is the same, but you do it from the inside the material. So now imagine you're inside the material like this. The light comes in, bounces off, and goes away. Because there's a difference between the refractive index of this material and this material, same as the air and the water, light can bounce if it's given a sort of sharp enough angle. And then what you do is you just sandwich the light between two of these surfaces, and the light will bounce back and forth. And so that's called total internal reflection. The easiest way to see it is if you've ever been in a pool. If you look in a pool and you go under water and you look across the pool, you'll see the reflection of the bottom of the pool and the top of the pool. That's because the light's bouncing the whole way along between the bottom surface of the pool and the top. What you'll also see if you look up is this big ring. And this ring's called an escape cone. Or it's a way to visualize the escape cone. What this escape cone is because as we know that light has to come in, right? So the light can come in at a certain angle. It'll also be able to leave at a certain angle. So if this reflection light is bouncing like this, if you bounce too sharply or too perpendicular, you can be emitted. And this has an angular dependence again on the refractive index. And it creates this cone where if the light is coming out at a specific area, you can lose the light. And that's the same here as underwater. Water has a high refractive index. There's air. You look up and you can only see light coming in from this cone. Everything else is dark because it's reflection. So the reflections occur in the dark spot and the light that can come in or out occurs here. So then the way the solar concentrator works is light will enter via an escape cone, or this entrance cone here. It'll have to come in at this angular dependence. It's then absorbed by a molecule. And this is what changes everything. Because it's now absorbed, it can be emitted in a different direction than that it was absorbed. If you just let it go through without absorption, it will just go right through. And that's why glass is transparent. At high angles, there's no refractive tendencies. So the molecule absorbs the light, right? And then when it emits it, it can emit it in any direction. And ideally, this direction emits it is at a sharper angle than this escape cone. And that's when it starts bouncing back and forth. Another problem, which I'll go through all the problems to get to the real problem, what we're trying to solve, is that once the photon's absorbed, you have two options. Either the photon decays, it just does non-rate of decay through thermalization, these vibrational modes that releases heat, you lose the photon, or it's emitted. And emitted is what you want to happen. Then if it's emitted, it has to be emitted at the right angle, right? If it's emitted too high, it's not waveguided, so it doesn't undergo total internal reflection, and it's lost. If it is waveguided, ideally you'd be happy. That can now bounce all the way along to our solar panel. But the problem is that there's a chance it can be reabsorbed by another molecule, because molecules can absorb light that other molecules emit, and then that bounces us back all the way up to the top. We have to emit the photon, and we have to emit the right direction, and we get reabsorbed again. So reabsorptions are the thing that's stopping this technology. It doesn't exist yet, it's not commercial, and so it's the big thing we need to fix. And so how do we go about doing that? This is why I had this picture here, this phycobilazone, big protein complex. It has blue proteins, green proteins, and red ones. And they, through our force to resonance energy transfer, which is a complicated way of transferring energy. Effectively, you have your energy states, right? Your excited state, and that excited state corresponds to the energy of an excited state in another molecule. And they couple through basically a dipole interaction, and then you can transfer energy through space without actually emitting it. But it just means that these blue proteins here can transfer energy to the green ones to the red ones. It always goes downhill. So blue is higher energy to green, higher energy to red. And the reason this is good is because you can reduce this overlap. So if you don't know what this is the absorption spectrum of a molecule and its emission spectrum. So in black is all the wavelengths that absorb light. In red is all the wavelengths that emit light. And you can see there's an overlap here where the wavelengths that it emits can also be absorbed. And that's where reabsorption happens. If you can transfer energy from one molecule to another, you can now have absorbing a blue molecule that emits as a red molecule. And the blue molecules can't absorb the red molecule's light. So that's what we're doing here. This is just a ratio between two different molecules. One has a peak here around 570, another peak around 530 here, the other molecule. And as you can see, as we go from 1 to 1, 2 to 1, 5 to 1, 10 to 1, and so on, we decrease this peak. But we're still emitting from this other molecule. So now we've decreased the overlap here, because this is what's absorbing, and that's what's emitting. And that's all we're trying to do in this slide here, was to make different structures in which we have a high number of high energy molecules surrounding a low number of low energy molecules. So this was a little polymer. You can see there's an N here, which means how many of these units are in there. So in the 4, N equals 4, there's 4 of these molecules in every arm. So it's a really quite big sort of star-shaped molecule, and they all absorb blue light. That blue light is transferred into our little red center, and that emits the red light. So now it looks like a blue molecule, but emits like a red molecule. Just like this. In this case, we just dissolved different dyes, but some blue, some green, and some red dyes. We're making the red one at a low concentration to make these crystals, and now they glow quite brightly as well. This was a polymer scaffold in which we attach different molecules like a pendant charm bracelet to the polymer, and as you can see, all the green molecules put energy into the red molecules and they emit there. Lastly, we used a silicon dioxide nanoparticle as a scaffold, again to put blue molecules close to orange molecules in this case to emit light. So it's all based on the idea that we can reduce this overlap by separating our absorption and our emission through different molecules, and then we can stop this reabsorption, and then we should be able to get to commercial solar concentrators. So just in summary, science is broad and fascinating, and with good foundation across the field in maths, in English, in scientific rigor and analysis, you can become a researcher in any field. And then one day maybe someone will take your picture and Photoshop you in front of the sun. Thank you for listening and have a good day.